Okay, this is the last video for section 4.4, and we are finishing up our curve sketching example. So here we are going to sketch the graph of this function that we've been looking at the whole time, the big reveal here. And remember that our function f of x was x to the 5/3 power minus 5x to the 2/3 power. And we are going to use all the information that we've been collecting about this function. And then if we get stuck or if we're not 100% sure what the graph is going to look like, we can incorporate some other points as needed. If we need to just plug a value into this function, that still works. You can still make a graph by plugging points in, but you do need to make sure that you incorporate the information that you found in previous parts of the problem. Okay, so first things first, this graph paper here doesn't have any axes, so let's start by making some axes. Okay. And if you happen to get a curve sketching problem on your test, hint, 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 I will provide this graph paper for you on the test. And so you would still need to draw some axes in. But that's actually kind of nice because then you can scale your axes however you like. So I think I'm going to make, let's see, I know we have one point here that went fairly low. We need to make sure we can incorporate -1, -6. That's a point on the graph. So yeah, let's see. 1, 2, 3, 4, 5, 6. Sure. I'm going to make 2 boxes be 1 unit, I guess. 1, 2, 3, 4, 5. Here we go. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. Okay, so if you don't want to label all of the everything on your axes, that's okay. Just make sure you label at least a couple points there. That way I know what your scale is. Okay, so let's see what we've got. All the way back up to the top. Okay, so first things first, the domain was all real numbers. Okay, so that just tells us that we shouldn't have any places where the function is undefined. Like there's not going to be any holes in this graph that don't have a value. The function will actually be defined at all of the points. And then part B, our intercepts here. We have an intercept at the origin and we have an intercept at 5, 0. So those are solid points to put on the graph. So let's go and put those points on our axes. 0, 0, and 5, 0. Okay, so this is a point on the graph and this is a point on the graph. Okay. Intercepts, could check. And back up here. Okay, there's no symmetry in this function. Darn, that could have helped us fill in one half of the graph or the other if we knew it was symmetrical. There are no asymptotes, so we don't need to go put any little dashed lines anywhere. Okay, would have had to do that otherwise. Now for the first derivative and second derivative, increase, decrease, concave up, concave down, that type of stuff. We are going to use these number lines, and here, I'll show you how. Okay, I'm going to transfer both number lines down to the bottom of this page. Okay, so our first derivative number line looks like this. F prime of x. we had found critical points at 0 and 2. Okay, you can track along with this. The first derivative was undefined at 0 and it equaled 0 at 2. And our signs for the first derivative went positive, negative, positive, showing that we had increasing and then decreasing and then increasing again. Okay, now right underneath that, I'm going to put another number line for f double prime of x and sketch in what was going on there. So here was our second derivative number line. Okay, got our inflection point on there. We'll put that on the graph in just a second. So we have negative, positive, positive. All right. Our main points of interest there were 0, where the second derivative was undefined, and -1, where the second derivative equaled 0. Okay, and then yes, our signs plus or minus went negative, positive, positive. Okay, showing us that we have concave down, concave up, concave up. Okay. And then the other thing we got from this last portion here was our inflection point, -1, -6. Let's put that point on the graph. -1, -6 would be right here. Okay, so that is an inflection point. Okay. Let's see what else we had here. So we've got our second derivative number line. We've got our inflection point. We noted on that number line where it was concave up, concave down. Oh, we haven't put these guys on here yet. So these also give us good solid points for the graph, local max and local min values. Okay, our local maximum was at 0, 0, which is already on the graph because it is our X and Y intercept. But this we can also label as being a local max. So that should be the highest thing in its little neighborhood. Okay. And then we had this local minimum where X equals 2 and Y equals approximately -4.8. Let's put that on the graph as well. So 2 and then approximately -4.8. I'd say that looks pretty good there. Okay, so that guy is a local minimum, the lowest thing in its little neighborhood. Okay, I'll just, I'll label our intercepts as well. Intercept and local max, and then this guy is just an intercept. Okay. So we've got 4 points on the function, and we have these number lines here. Okay, so here's how you use the number lines. All right, if you take your points of interest on both number lines, notice that 0 is a point of interest on both of them. I'm going to kind of put a little dashed line up here for -1 and put a little dashed line going through for 2 right there. Okay, I'm going to indicate also that there are essentially 5 different little intervals going on here. All right, first this one from -infinity up to -1. Okay. And in that interval, the function is concave down for sure. And it's also increasing because that interval is part of this portion that was increasing. So just that part, still increasing. Okay. So I'm going to actually indicate a little plus increasing there as well. Let's just kind of corral this guy and move it over a little bit. Okay. So both of those parts are increasing. Okay, so, oops, I was just trying to make that a little larger and didn't like it. 1 second. Increasing. Okay. So yeah, for that first little interval here, from negative infinity to -1, the function is concave down, or sorry, concave down and increasing. Now remember way back to the explanation of this curve sketching process? We had this handy dandy table right here that shows us generic curve shapes. Now, the part that we're looking at, the interval we're focusing on, is concave down and increasing. So concave down and increasing, those intersect right here. And so that shows us the shape of the graph that we're going to have. Okay. So our graph is going to make this type of shape on the interval from negative infinity to 1. Okay, so let's go put that in. Swoop, swoop, swoop. Back down here. All right, so it's going to have basically this type of shape for concave down and increasing. Okay, now I'm just going to recopy that table down here so that we don't have to keep going back up to the previous page every single time. Okay, remember it's a grid of 4 squares, decreasing, increasing, concave up, concave down, and it goes like a U shape up here, and then like a V shape down here. Okay, so we've got our increasing plus concave down there, and then look at our next interval from -1 to 0. The function is concave up and increasing. So that is going to be concave up, increasing this type of shape right here. Okay, so that's going to have this type of shape. And then in our next interval, that's going to be here from 0 to 2. Okay, the function is concave up and decreasing. So concave up, decreasing this shape right here. Okay, so that is going to have this type of shape generally. And in the last interval here, from 2 to infinity, notice that this is still in the portion that is concave up. So you can add another extra little positive concave up right there if you like. And so in that interval, the function is concave up and increasing. Okay, so concave up, increasing this type of shape. Oh, that's a repeat. We already saw that one, but you can use these shapes more than once. It's totally fine. Okay, so those 4 shapes tell us the general pattern or general look of the graph in those intervals. So you can basically fill in the graph here, okay? Knowing that from negative infinity to -1, we're going to have this type of shape. And -1 is right here. Okay, so it's going to have that type of shape and it's going to run into the inflection point. So you can, plug in another x value over here if you like x equals -2 or -3. But the general idea is that the shape is going to look something like this. Okay. And that's really close enough for what we're trying to do here. Make that type of shape. And then on the next interval from -1 to 0, we are going to have this shape right here. So it's going to curve upward like that from the inflection point up to the local maximum. Now remember, that is a local max, so it should be the highest thing in its little area. So we'll curve up to that point. So we know where our curve starts, where our curve is going to end, and what the shape of it looks like. So make that little upward curving type of shape. Yeah, it goes pretty steep. That's a little wobblier than I'd like. Let's see if going like this will help. Okay, there we go. That's a nice one. I like that. Okay, it's kind of stretched out as you can see, but it does still have that concave up type of shape to it. And it goes from the inflection point to that local maximum. Okay, next interval. From 0 to 2, the function is going to decrease and be concave up. So we have that type of shape. Our function in this little chunk is going to start at the local max, and then it's going to take that shape and curve down until it hits the local minimum. Okay. So, because that is at x equals 2. And so we're going to curve, use that shape until we hit our local minimum value there. All right. And then for the last part, our interval from 2 to infinity, the function is concave up and increasing. It has this type of shape. And we are going to be starting from our local minimum right here. We're going to be curving up, and you have to make sure that you pass through your intercept, because an intercept is a point on the graph, so your curve needs to go through there. And then we also found when we were doing our limits for the horizontal asymptote type of thing, there wasn't a horizontal asymptote, but we did find that our function approaches infinity as x approaches infinity, so it's just going to shoot off after that. Okay. So that part in highlighter is basically what we're going to sketch in for the rest of this function. Okay, let me do it in pen here though. So go from your local minimum, take that upward curving shape and put it in. Pass through your intercept at 5, and then indicate that your function is going to go off towards infinity. And that is the graph of this function. So that is what x to the 5/3 minus 5x to the 2/3 looks like. Very cool. Now, I guess I could see if the computer will graph this as well. Sometimes it likes my writing, sometimes it doesn't though, as you guys have seen in multiple videos. So let's see, 5x to the 2/3. All right, let's try it. Let's see if it likes that. Hey, it did. First time. Graph in 2D. Hey, that looks like our graph. If you zoom out a little bit, well, the inflection point there is not very noticeable, but it should be in there. Boy, that's pretty, it's pretty linear looking, but we know that the inflection point is there. They do have a slight curve to that. So yeah, I guess there is a bit of concave down, concave up there, not as pronounced as my sketch, but especially like, look at that sharp corner there at the origin. We got that just from our derivative information and the fact that the origin was a local maximum. And this part with the local min right there looks pretty spot on as well. Yeah. So pretty cool what you can do with just algebra and then first and second derivative information. We can make a pretty sweet graph. All right, cool. So that's how you do the curve sketching process. So there's still one problem left in this sections notes, and I'm going to leave this one for you guys to try out so you can try the whole process from scratch. And I mean, I'll finish out the notes for this, and then you can check and see, you know, if you did the process correctly by checking through the notes, which will be posted on Canvas. So check those out. But first, try and do this problem to sketch that function. And really try all the steps first. Don't just plug this into the calculator and be like, oh yeah, that's what the graph looks like. Really try the steps. See if you can put everything together.